Hello, everybody, and welcome to our Cumene chemical plant design process project. We are Team 19 Dawn Dynasty, and we're happy to be presenting our process today. So, just a little bit about our team. My name is Kevin Hoxha. I'm a senior as well as along with all of our other team members, and after graduation, I'm still currently looking for a position, but I'd like to be somewhere in the research and development world.
Hi, this is Yizhou, and I'm going to the grad school, and it seems like I can't go to Purdue for my master degree.
Hi, I'm Tim Phillips. I'll be graduating after graduation. I'm going to be working at Air Products in Allentown.
Hi, my name's Ethan Freiss, and after graduation, I'll be working with Eurofins in Lancaster, Pennsylvania.
Hi, I'm Neil Tufano. After graduation, I'll be working for a water treatment company as a technical sales representative.
Our small size as a company and talented technical staff has allowed us to respond quickly to the needs of the market and develop and build safe, cost-efficient, and highly reliable processes. As a company, we benchmark best in industry practices and implement them into our work process on a continuous improvement cycle. For example, this project was managed through a stage gate system, which allowed us to allocate our resources most efficiently and meet the needs of our customers both internally and externally. We utilized a process development readiness index for all of our capital cost process projects. Knitline Chemicals currently has a few sites in the United States, and this specific plant was evaluated to be built in the U.S. Gulf Coast location, which focused on the production of cumene. The Gulf Coast location was selected because this is a location where benzene is readily available and produced, and propylene is easily accessible via pipeline for the plant to produce cumene product and can be distributed to consumers. Knitline Chemicals' R&D department has developed a new catalyst for producing cumene from propylene and benzene. This was one of the main driving points for evaluating the economics of the process, because the new catalyst has a much better selectivity to cumene than the competition. However, on the downside, this new method may require higher capital or utility cost. There are two main reactions that occur in the process, which are the primary reaction, which alkylates the propylene molecule onto a benzene ring and forms cumene. One of the side reactions that occurs in this process adds another propylene to make diisopropyl benzene, which is utilized in the secondary reaction of this process. This secondary reaction is a transalkylation reaction, which takes the DIPB and transalkylates it in the presence of benzene and a different catalyst to produce additional cumene. The cumene product from the benzene and propylene feed streams was desired at a purity of 99.9% weight fraction and can be sold at 42 cents per pound at a capacity of 390 million pounds per year. The process needed to be designed to meet certain hard specs of the 99.9% purity cumene and capacity of 390 million pounds per year while maintaining economic feasibility. There were also various other hard and soft specs in the process which the design needed to meet and will be discussed later in the presentation, such as the ratio of materials in each reactor and relating to the recovery of the products of the process. Overall, the process we designed was able to achieve a sufficient purity of the cumene product feed of 99.9% purity and a capacity of 390 million pounds per year. And here's Neil to talk more about the details of the process we designed.
So the first half of the process includes the separation of impurities from the fresh feeds and the main reaction producing cumene. Prior to the mixing of the fresh benzene and propylene feeds, the benzene stream passes through separator 1 to rid of inert toluene from the process. The benzene outlet and propylene stream are mixed along with the benzene recycle stream before entering reactor 1. The main reaction occurs producing cumene and multiple byproducts, including DIPB, cyclohexane, ethylbenzene, and O-terphenyl. The impurities within the fresh propylene feed are separated out from the process in separator 2. Benzene and other hydrocarbons exit the top of separator 3 and flow into the transalkylation reactor. The second half of the process includes the transalkylation reactor, the recycle stream, and the purification of the cumene product. Heavy molecules exit the process via the bottom stream of separator 4, and DIPB is separated from the top stream via separator 5, before combining with the benzene stream from separator 3 and flowing into the transalkylation reactor. The cumene product from the transalkylation reactor is then purified and separated from other species by passing through separators 6, 7, and 8. Separator 6 includes a split purge and recycle stream to limit the buildup of benzene and cyclohexane that is recycled back into the first reactor of the system.
Yes, so when looking more into the hard design specs, we noticed that despite limitations, we could only not meet 3 known specs. So first looking into it, the cumene output must have equaled 46,428 pounds per hour. And in our process, we have a design spec that gives us this exact amount. Looking into the purity of cumene coming out of the product stream, it needed to be 99.9% weight fraction of cumene. And this spec, as you can see, was met. We reached a purity of 99.93. Looking more into reactor 1, we needed to have a mass ratio of 5:1 of benzene to propylene going in reactor 1, which we were able to meet by using a design spec. And for reactor 1, it was determined that hexane must be at 3,000 parts per million max, toluene at 1,000 weight parts per million, and cumene at 1,000 weight parts per million. All of these specs were met by optimizing the process and utilizing the design specs in this process. Going into reactor 2, the trans reactor, the feed molar ratio into reactor 2 must have been 6:1 for benzene DIPB. We were not able to meet this spec. We believe our first reactor was not producing enough DIPB, and the amount of benzene that was recycled into reactor 2 combined with that small amount of DIPB reached a mole ratio of 42.6, and it was very difficult to decrease this said ratio. Achieving this ratio would require purchasing more benzene fresh feed, which would undesirably increase the cost. Looking more into the transalkylation reactor, cumene should be a 1% weight percent of the feed-in. Butyl benzene should be 20% weight, and the heavy should be 500. In our process, the butyl benzene and heavies were met. However, due to dysfunction in reactor 1 and inability of separator 4 to separate the products as desired, a large amount of cumene was sent into this reactor, which did not fit the spec. As said before, the cumene weight fraction should be below 1%, but it was at currently 27.8%. Fixing this would require adaptations to the entire process, which would ultimately cost a lot more money. Onto the next, we were looking more into the soft specs, and we were unable to meet some of the design specs, although we tried many different simulations and altercations to the plant design. The cumene recovery should have been 99.5%, but we were at 95.58%. This is because some of cumene leaving out of our stream 15 when separated by the purge stream to prevent it from being recycled throughout the reactors. And changing this process would require separators being altered, which would affect the final purity and cost a lot more money. DIPB recovery should be 95%, but our value is 25.69, so it was not met. This is due to the small amount of DIPB that was produced, which was eventually sent to waste in order to purify the product. If we were to meet the spec, the product would not be purified and not be able to sold. So we prioritized meeting the initial specs, then meeting this spec. Benzene directly to waste should be around 2%, where we were currently at 11.29%. So this was not met. In order to purify the cumene product, some of the benzene needed to be sent to waste to obtain this desired purity. If we attempted to meet this spec, it would lead to less pure cumene product stream. The overall selectivity of cumene should be 96. However, we were unable to meet the spec and status selectivity of 89.8%. This could be a factor of the dysfunction with reactor 1, and fixing this would increase costs. Looking at temperatures of these different separators, the goal was to have everything limited to 400 degrees F. Temperatures should be kept for the reactor below 400, which was done, but in the separators, they must be kept below 470. And every single one of them worked besides separator 4, which is at 529 degrees Fahrenheit. We decided to continue without meeting the spec because the column would only run at a limit of 23 psi before stages began to dry up. This would therefore result in costs that would arise from trying to lower this temperature and making it not viable.
All right. The feasibility of our cumene production process was determined by performing an economic evaluation. So this included calculating our capital costs, which include and represent the cost of equipment for the process, construction of the plant facility, and other costs along those lines. So those costs have been split up through the first 3 years of construction. Next, we have the operating costs, which are the year-to-year costs of running the plant. That include purchasing feed streams, so raw materials, costs of supplying power to the plant, and utilities. And finally, we have the fixed costs, which include things along the lines of employee wages, repair and maintenance that needs to be done over the lifetime of the plant, property tax, and insurance costs. So the capital costs of the process system were estimated for this process using Aspen Economic Analyzer. So that software was used to determine the cost of each piece of equipment involved in the process. And so that equipment cost is represented by our IBL in the blue there, the blue portion. And as you can see, it's responsible for most of that, almost 100 million. The OBL, or outer battery limit, represents all offsite expenditures, including things like storage. And the last two pieces are team/other and escalation and contingency, which make up, like I said, the last piece. And the total for those four rounds us to just under 100 million on capital cost alone. The operational cost of the plant is a massive piece of the financial implications of running, of course. So all of these figures are averaged over the first 15 years of plant life. So as you can see, our raw materials cost dwarfs the actual utility cost, which makes sense. So the raw materials include feed streams, and as it says over there, just all of our chemical costs and DI water, including catalysts. And the utilities include mostly just the steam that we need for the process and the cooling water. Now, the additional fixed costs for the process include labor and other crucial aspects of operation. So these four specific categories give us an annual total of about 13 million. Now, labor and overhead goes to any wages or compensation being given to employees. So, and while overhead includes costs overlooked by wages such as marketing and administrative costs, repair and maintenance is an average figure of the cost to maintain our plant running at our desired capacity levels. Property tax is roughly $3 million annual fee that we must pay. And finally, insurance is about less than $1 million, and it represents our annual insurance policy to be maintaining our operation, which lands us at our total of 13 million.
So by performing a cash flow analysis, we determined that the process will not be profitable. When looking at our cumene product price at 42 cents per pound, we ran the cash flow and determined that our process was running at about a product of 42.65 cents per pound. Obviously, that is a more cost for the process than the cumene product, so we'd be losing money initially. And at this current point, there's a net loss in the process, causing us to lose money immediately.
After evaluating the cash flow analysis of the various different costs involved with the process, it was determined that the overall process will not be profitable if it were to occur under the current project design specifications and requirements. As a result of this, the after-tax rate of return is negative. The net present value over the 15-year cycle of the process would be negative $78 million. The process would also result in an average cash flow of negative $191 million.
So as a result, we do not recommend to start this project of our plant until the cumene price is expected to raise to over 47.45 cents per pound. Well, we can reach 50% ATROR goal, while the other prices are remain unchanged or lower. So our process requires several things to change in order to get it profitable and recommended by our team. So first of all, we could use liquid extraction instead of distillation tower. So that would save raw materials that is purged out. In our case, we could save about 260 pounds per hour benzene. That is about 27 cents per pound. And overall about $70.21 per hour. And annually it will cost $1 million for building a liquid extraction tower, but it can save about $590,000 a year. The other alternative change is to do the toluene purification, so we can make profits through one of our waste stream, adding a secondary distillation column in order to purify the toluene waste stream to a purity of 99.8%, at which the team will be able to sell the stream for 20.8 cents per pound. It shall be evaluated whether an addition of the distillation tower, as well as the cost of operating or maintaining the tower, is less than the profit. If this plan was implemented, approximately about 2,000 pounds per hour of toluene could be purified into a profitable stream. A rough economic evaluation shows that the profit of about $3 million a year would be gained by selling those purified toluenes. And I think that's all for our today's presentation. If you have any questions, just contact us or comment under this video. And thank you guys for watching.